All right. So next quick demonstration here is that if I wanted to do it, I could potentially rewrite this function in a slightly different way for the sake of the argument here. If I just say, okay, let's initialize index back to 0, or even, you know what, even make it simpler. Make it like something, look something like this. Just erase this, I guess, for now. While how many? Right? While how many? How many is probably not a 0, so the loop begins. And inside that loop, I would like to print my values. For example, I can just simply say, okay, dereference pointer. So the pointer is the pointer to the first element. Then say increment pointer, so that we have a chance to display the next integer in memory, but also decrement how many. Right, so that how many is now used as a loop controlling variable, basically saying that okay, they told us how many. As soon as we hit like 0, then let's stop. So let's see how it works. Right. So if I print just like a single new line right here to separate. This type of output a little bit, something like that. Let's build this and see if I made any logical errors in trying to use this loop to actually should start this again. All right, Control F5. So here it is. Doesn't seem to be any different. So it's still 1, 2, 3, 4, 5 because it's the same idea. I figured a way to initialize pointer to specify where is the address of my integer. Then I was also told how many integers to print. Oh, I'm looking at the recording, right? So I was told, let me kind of close those windows that were open prior to this. Right. So then I'm just saying that let's dereference pointer and print the value. It means that go at this address, extract the value. This is what dereference means. And then increment address, of course, with respect to the pointed data type. So increment is different for integer. Increment would be different for character, double, and any other data type. And then decrement the counter or the specified number of elements to print. Okay, so I know this is a little bit of a lot of different syntax samples and so forth. But again, we keep kind of walking around the same syntax. There is a way to create an array, that's fine. There is then a way to access individual elements, and guess what? Now we're accessing memory, and instantly we're using the syntax we already used many times. This is an array name. This is an index into an array. We know exactly what's going on. This must be an address. This must be an offset from that particular address. And the array also knows what type of elements it stores. So every time you say 0 or 2 or 4, it knows exactly to which element to jump and go ahead and display it. Now, a few notes about other parts of the syntax. I will copy and paste this. The initializer allows you to abbreviate the list, the initialization list. For example, if I say 0 here at the end, the missing, so I was able to initialize like 3 elements, and then I said 0, then those 2 were not initialized. By default, the remaining not initialized elements in the array will be initialized to 0. So this is equivalent to this. So those will be 0. So let me save and try to run it. We should see 1, 2, 0, 0, 0 as a result of what we print right here. So now 1, 2 is initialized. The rest is guaranteed to be initialized to 0. Therefore, most people, if they just want to initialize everything to 0, say this. That means that everything is now initialized to 0. Or some people actually do even this. It's like empty initializer means initialize everything to 0. In my style, I prefer to do this. But we can try this. So that should print only zeros. There you go. It's just all zeros that are being printed inside that array. Okay. So these are the possibilities. However, if we don't do this, and if we do not initialize our array, it's going to contain garbage. The absence of initializer means no initialization should be taking place. So who knows? We know better, right? So in this case, if I run this, now the compiler prints the message, "Hey, warning! Uninitialized local variable temperatures is being used." But anyway, so what it does here? Runtime check failure. The variable temperature is being used without being initialized. Ignore. Okay. so the debugger was invoked to tell us, hey, you're really sure you want to do this? And we said, yes, we want to do this. And we ignored. But these are the garbage values, right? So which were still there, and so the code is legal. We just never initialize it. It's kind of nice that we once in a while get those warnings. We should probably appreciate those warnings and pay attention to them. So, but here nothing was initialized. The limitation of this array. Well, like I said, for some reason I may wanted to use a set of integers and use them in this manner, and every single one is accessible through index, and this syntax really kind of demonstrates it really well. This is slightly different, more pointer specific. Those two examples are exactly the same, but just the driving force behind those two samples is a little different. Here I'm saying that I understand that this is an array, and I'm accessing individual array elements. In this example, I'm saying that I know I have a block of memory and I have a pointer. So I can actually navigate this pointer within that block of memory and move from place to place, and occasionally print what am I pointing to. And then I also control the loop by decrementing the counter, so it goes to to 1 less, 1 less, 1 less. As soon as it becomes 0, I'm out of the loop. And if someone passes 0 to this print function, I'm in trouble, right? Because oh no, I'm not in trouble, because this will be 0 and I will never enter the loop. So that should be a problem. Okay. Because sometimes you have to look at those boundary values to make sure that they're okay. -1 would be bad news. So I could probably try to put an assertion here that it's 0 or positive or something like that. Yeah. So defensive programming, always a good idea. So the limitation of this array, and we use it, would be this. What if I also, let's switch to this example with characters a little bit, and say, what if I wanted to ask user, right? We have this integer how many, whatever, right? So if I said I have a variable, and I can ask user to ask the user, say, how many integers you want, and use a variable to create my array. It's not going to work, because what happens is this. We know that each function, such as main, right? Main, in our case, then print which we also call print, they all get their local memory, right? So the local memory, the so-called frame stack or activation record, is constructed even before the function executes. In that function, we create our integer variables, we create our double variables, and all other objects. They're all created here. When we call print, its own stack frame is constructed, right? And whatever input parameters are, they're basically passed in this location. So essentially, let's refresh this memory, refresh this kind of set of ideas that when a parameter is passed to a function, it is actually, or set of parameters are pushed on the stack even before the function is invoked. When the function is invoked, its opening brace basically constructs the frames, its own like local variable placeholder, which is called stack frame. And what happens that magically the function parameters are found right here in those places where the parameters were originally pushed by the caller. So the function, while function executes, the parameter are already there. They're present, they're completely initialized, and they're all ready to go. Good news, right? At least in one particular calling convention, that is the way parameters are being passed. So then when function returns, all of this gets erased and we're back. So now imagine that we have an array, and I will again redraw this to make some more space for what I'm trying to draw here.